Hello,
Hi.
how are you doing?
I'm okay. Yeah.
Chris is.
I guess I'm a little early.
I know you're almost on time. We're waiting for other people to join in, and Chris is coming a little late, so I'm hosting the session today till he
Okay.
joins.
I probably don't need to be live on this.
Okay. Yeah. Anytime you have questions, you can always pop up. Hello.
Yeah, I'm just trying to figure out where the
How are you
chat.
doing? Go all the way to the top. Up the
Okay.
screen.
Chris is. I guess I'm a little early.
Right. You're almost on time. We're waiting for other people to join in. And Chris is coming a little late, so I'm hosting the session today till he joins.
I probably don't need to be live on this.
Okay. Yeah, anytime you have questions, you can always pop up. Hello.
Yeah, I'm just trying to figure out where the
How are
chat.
you doing? Go all the way to the top.
Oh, this is
Up
weird.
the screen. Chris is
I'm a little early.
right. You're almost on time. We're waiting for other people to join in. And Chris is coming a little. I guess we'll give a couple of more minutes. If not, we can start. Let me call somebody else. Otherwise, we'll start. 1 minute. Okay, I think looks like we have the required audience to start off. What Chris told me today was to start off with section 2.2 and go up to section 3.2, and assuming that people were able to read these sections. I'm sharing the online version of MIT's category theory for scientists, so we can all look at the same thing and quickly review this. These sections basically cover something not very complicated, but some new concepts pretty nicely written to explain more advanced topics in category theory in a later stage. The start of this is section 2.2, which is a section on commutative diagrams. We have sets like A, B, and C, and you have functions f and g. When A can go to f is a function that takes from A to B, and g is the one that takes from B to C, then you can have a direct arrow from A to C, a new function, and this will become entire diagram starts commuting when G composed of F. That means you start with F and composed with G will be the same as H. It's something we've seen in the past, so same concept. There's some very nice applications of this, and a different commutative diagram has F going from A to B and G going from B to D, and H is from A to C, and there's an identity type of I that is going from C to D. Again, the solution to that, the whole thing commutes only if G composed of F, that is, you start with F and compose with G is same as I composed with H. That means start with H and compose it with I. So end up with D. He's got a nice example from physics here. If you have a system here and some problems, some state you want to predict in future, then you can either go to Lagrangian approach or Hamiltonian, both should give the same result. So this diagram commutes. And here it goes to different ways of drawing the same diagram. And now he introduces something very unique for this book called Ologs. Ologs are, if you're a computer scientist, are they sort of look like a bit like a UML type of diagrams. And there's one such diagram here. And to start off Ologs, it starts with something called a type. Type is an abstract concept where type is represented with a box, and a man means consists of all the man basically, or an automobile means talking of a class of automobiles. So his basic assertion here is that inside the box is going to write a single indefinite noun phrase. So then you can also have sentence like this, a pair AW where W is woman and A is automobile. So that forms a type, and types with compound structures are the ones with a bunch of statements inside, where you can write something like a pair M, W, where M is a man and W is a woman. And he has some good practices in how to write these types. After the types, he has something on aspect. From mathematical point of view, aspect is a function, and it looks like, at least from the way I read it, it looks like one-to-one function basically. So a woman is a person, and a molecule has molecular mass in Daltons. It is Daltons, which is some positive number, real number. And then he contrasts his aspects, which are functions, with the invalid aspects, where a person has a child is an invalid cause because the person can have multiple children or no children. So it's really looking one-to-one between person and child. And what he's doing is afterwards is to read the aspects and facts as English phrases. So a book has as a first order as a first order a person. It reads like that. And I believe this is all just to sort of make the latter analysis of inferences much more easier. So you can have multiple more complicated diagrams. A child is a person, has as parents a pair, WM, where W is a woman and M is a man. And a person has a birthday, a date that includes a year. Why is he doing that is to sort of develop some sense of what diagrams really commute between these things, and to write some practices. So from practice we can sort of take a statement and translate into these diagrams using types and aspects, and get some facts together on that. So for example, this is one example of a commuting diagram for using his Ologs, where you start with DNA sequence. It can be transferred, is transferred to RNA sequence, which is in turn translated to a protein. And you can also say DNA sequence as codes for a protein. So this is a commuting diagram. Whether you go like this or like that, you got the same information encoded inside here. Then he got a bunch of exercises, and he gave a formula for writing facts as English instead of just putting it in the C, for example. And there's more than his text out there. His examples are very illustrative of how he wants to do it. For example, you have this diagram here. A person with a type has an address. This means it's a aspect. And person lives in a city, and an address is in a city. So both these are aspects, in other words, functions. So the way he's going to sort of translate this two-step process, he starts with a variable called x. Given x a person, he says consider the following. We know x is a person, and we know he has an address, which is in a city. Then we call it p of x, which is like a preposition, which is saying a person lives in a city, has an address who's in a city. And we also know same person x who lives in a city, so we call it q of x. So because this diagram is commuting, we have fact is whenever x is a person, we have the preposition p of x is equal to q of x. I call it a preposition, we can call it a function, whatever it is, basically. But when you translate whole Olog into English, it comes like the person x has an address which is in a city, and the city x lives in. So it's got more complicated Ologs, and then he talks of images. Images are again like functions. Anybody with basic math background know what it is. That's something he's describing in more in terms of Ologs here. And for example, in the typical theory here in the category, in the sets here already introduced two terms. One is called domain and codomain. Domain is when you start from where you start from. Codomain is where you end from. So function is one that's going to it takes a subset of elements from codomain, and that are hit by a function. That's what it means basically. So for example, f of z to z has 2 star z means now we have image is set of all even functions. So he has again, if you take an aspect, if you consider like a function, it has an aspect from a person to a mother, saying p to p has a mother, and it has an image saying that now m is equal to image of f, which is a mother. That is the end of this chapter. Yeah, and if you go next, he's going into more advanced topics with set theory, which is it's just something called universal property. So before he starts universal property, he defines a product of two sets, x cross y, and it is an ordered pair x comma y, such that x belongs to x and y belongs to capital Y. This is something we always see in mathematics quite often, and no surprise here. And this function has two projections. One is called phi1, which is takes x cross y, that means pair of x y, and projects to x, and phi2, which is x cross y and projects to y. This, if you take coordinate geometry, it's like coordinate projecting into x-axis and projecting something into y-axis. So the diagram looks like this: x project to xy, and it's got a very simple example here. There is a set consists of numbers up to 6, and there's shapes here, and cross product is nothing but pairing of these two things together, all the combination of pairs. And there's got a very small example. Exercise says how many elements does a set ABCD cross 1, 2, 3 have? It's 4 times 3, 12. So it naturally falls up. And whenever you take two cross products, you can also extend to 3, 4, and further. So if you take 3 cross products, it's called called a triplet basically. Then he's got a bunch of exercises on which of these diagrams commute, and obviously for any for any diagram to commute, the end product should be same, whether you take this path or that path. And if you sit down and work it out, only the third one commutes, the first two don't commute. So here he defines the first critical, first more advanced topic in this chapter, which is called universal property. Basically what that means is you have this x cross y as a starting point, you have projections to x and projections to y, and you have function f that starts from a and arrows to x, and a function g that starts with a and arrows to y. So what this universal property purports as such is that you can have a function or a function like object that starts in A and dots all the way to x cross y. And its definition is within angular parenthesis, starting with A, ending with x cross y. And the property is that you take the projection of f, angular within f comma g, you get f, and phi2 of f comma g, you get g. And within f comma g is the only function for which this is so basically. So essentially, again, the fundamental is that you have x comma y here. So x cross y, you got two projection operators, and we got a function that starts with a, ends with x, and ends with g. Then you can define a universal property called f comma g that starts with a, and ends all the way in x cross y. There are some very nice examples it gives next few things, and one example here is that he's got some funny pairs here that goes to R with the property z of funny pairs equal to 0. Then we take this universal property, it guarantees a function called R cross R, which is nothing but origin in the R squared space. So it's got a few more examples and a little more complicated examples of these products. And the same products can also be used for O-logging. For example, you have two pairs, you can do the O-logging of products again. There's a few more examples of it. Then it defines a new concept called coproduct, which is like a union, but very different from union in the sense when you have same element in both the sets, you label it. You don't make one element. You just label it as two different elements. For example, in a simplest sense, if x is equal to ABCD, y is equal to 1, 2, 3, your coproduct is nothing but a combination of both, which is exactly like a union. But if you take x, hello? Any questions? So however, if you take X coproduct X, which is symbolized as this, in that case, what you do is you go on writing A1, B1, C1, A2, B2, C2, D2. So in other words, you're having what you call a different labels. ABCD you take and label it twice differently. He has that same coproducts applied to his Ologs as well as a nice example how it applies basically.
Yeah, I don't understand. Is anybody else here?
Hello? You guys okay? So far he has done a universal property for product of sets, and here he is doing a universal property for coproduct of sets. Again, the concept is you have a function, you have sets x and y, and you have function that is from x to a, and g is from y to a. Then your universal property for coproduct x y is nothing but a direct dotted line fg that goes to a. And for x and y now are included. They call generally I1, I2 are like inclusions, but we call it I1, I2 into coproduct. So this diagrams are commutes. That's what it means is whether you go like this or like this, you're the same. You end up the same. So the basic property is that we can define a function. He has different way of writing this universal property for a coproduct. He writes f and g in different, same line like this, and it sends x coproduct y2. And if you take this and project to I1, you come to f, and project on use I2, you jump onto g. So it's got some nice examples for products, including something to do with airplane seats and all that. I think that's where Chris asked me to stop, so I'm going to stop here. I guess from 3.2 onwards will be next session, probably on next Monday. So any questions? Looks like there are no questions at this point. So thanks, guys. I'll see you guys in my next Monday. Okay, bye.